At this point, we want to explicitly bring in our rank nullity and invertibility conditions and see how these play nicely together. One of the requirements we saw earlier is that a matrix, we're talking about invertibility of matrices specifically, it only makes sense to ask about invertibility if the matrix is square. If it's not square, we know for sure it is not invertible. So not square immediately implies not invertible. However, it turns out that even if you have an n by n matrix, not even all of those are going to be invertible. So let's walk through some of the concepts we've seen with matrices and the rank and nullity and see how this plays out. So if A is an n by n matrix, it has n columns. That's exactly what the second number here means, the number of columns in the matrix. To be invertible, the transform that goes with A must be 1-to-1 and onto. That means the matrix A's kernel has to be, well, we already said this earlier, if it's going to be 1-to-1, that's the injective. And for a matrix to be injective, its kernel must be just the 0 vector, nothing else. Well, that then is 0-dimensional. So what's the rank of A? And remember, the rank is the number of linearly independent columns. So we're all focusing on the columns here. The rank of A, the number of linearly independent columns, what does that have to be? Well, we know it has to be n because of the rank nullity theorem. The rank plus the nullity has to equal the number of columns. And we know the number of columns is n. We know the nullity, the dimension of the kernel here, is 0. So the rank has to equal n. And that tells us right away that the columns of A must be linearly independent. We have all the columns in our matrix being linearly independent guaranteed. If any of these conditions here are true, then we're guaranteed that our function is going to be invertible. Our matrix A is going to be invertible. So we can look at the columns, look for linear independence. We could look at the rank, though that's less obvious. We could ask questions about the kernel. If we can answer any of those questions, we know immediately whether our matrix is invertible or not. Let's see that with an illustration. Here are 3 different matrices, and we're just asking whether they are invertible. Do they represent standard matrices of transforms that are invertible? Take a look at them for a moment, and then we will check in. All right, so let's do the easy one first. This is not square. This is a mapping implicitly from 3 dimensions. If we do the matrix multiplication, this is a mapping from R3 to R2, and we know that that cannot be invertible. There's just no way. So we would just hide that for a moment. It's not square, therefore it is not invertible. Done. How about B though? If we look at B, B is a square matrix, so let's check that off. It's at least a candidate. However, if we take a look at the columns of B, we see the columns are not linearly independent. They're multiples of each other. Independent. That means the kernel will be non-zero, not just the 0 value, and blah, 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 all the other associations. At the end of the day, B is not going to have an inverse. It will not be invertible. Whereas to compare and contrast, here we have a lovely matrix which is square. And I'll try to make my writing more legible. I do apologize. And the columns of A are linearly independent. And so the kernel will be just the 0 value, all the other knock-on effects. That will mean that C, sorry, this is C, I called it A there, columns of C is invertible. If we take, this is R2 to R2, if we imagine this as a transform from 2D to 2D, it'll map points, all the points in R2 to new points in R2, and we'll be able to undo that transformation. Now, hopefully your antennae went up there a little bit and said, well, that's great if it's 2-dimensional because it's really easy to tell the difference between linearly independent and dependent at 2D. You're absolutely right. If we went up to 3x3, 4x4, 5x5, we would not just be able to look at that matrix and see the linear independence. We'd have to do RRAF type stuff to determine that for sure. So what we have are useful tools so far in terms of identifying invertible matrices versus not invertible, but we definitely need to explore further to get reliable tests for this kind of thing.